Consider a chemical reaction A to B conversion having an activation energy of 50 kilojoules per mole at 20 degrees Celsius. Let us calculate the fraction F e to the power of minus EA by RT. As EA should be expressed in joule per mole, 50 kilojoules per mole becomes 50 into 10 to the power of 3 or 50,000 joules per mole. The temperature should be expressed in Kelvin. Therefore, 20 degrees Celsius becomes 273 plus 20 equivalent to 293 Kelvin. R equals to 8.314 joule per Kelvin mole. On substituting all these values in the fraction, it looks like e to the power of minus 50,000 divided by 8.314 multiplied by 293. This fraction may be calculated by using e to the power of x button in scientific calculator, and on calculation the f value works out to be 1.20 into 10 to the power of minus 9. This means that if the reaction has 100 row or 10 to the power of 9 collisions, what number divided by this value equals to 1.20 into 10 to the power of minus 9? This number would be 1.20, which means that for every 100 row collisions occurring in a chemical reactions, only 1.2 collisions are effective collisions with energy in excess of activation energy and which undergo the reaction. Now we shall reduce the activation energy of chemical reaction from 50 kilojoules per mole to 25 kilojoules per mole, maintaining at the same temperature of 293 Kelvin. On redoing the calculation, the value of fraction equals to 3.48 into 10 to the power of minus 5. This value is same as 3.48 into 10 to the power of 4 or 38,400 divided by 10 to the power of 9. This indicates that for every 100 row collisions, the fraction of molecules having enough energy to react is equal to 38,400. From these two cases, it is clear that on lowering the activation energy from 50 kilojoules per mole to 25 kilojoules per mole at constant temperature, the fraction of molecules which are reacting increases from 1.20 molecules to 38,400 molecules. That is, 32,000 more number of molecules are able to undergo the reaction having lesser activation energy. Thus, it may be concluded that as activation energy decreases, the fraction of molecules to react increases. For the same reaction, we shall calculate the exponential factor by keeping activation energy of 50 kilojoules per mole constant and increase the temperature from 25 degrees Celsius or 298 Kelvin to 300 Kelvin. At 293 Kelvin, F value on calculation works out to be 1.20 into 10 to the power of minus 9. Similarly, the fractional value at 300 Kelvin on calculation equals to 2.40 into 10 to the power of minus 9. From these two values, it is clear that for every 10 degrees rise in temperature, the fraction of molecules undergoing the reactions are doubled. Now, let us apply these observations of activation energy and absolute temperature in Arrhenius equation. From the Arrhenius equation, rate constant is directly proportional to the exponential factor e to the power of minus Ea by RT. That is, rate constant increases with the increase in the F value. By lowering the activation energy value and increasing the absolute temperature value, the F value increases. That is, the fraction of molecules which are reacting increases. Thereby, the rate constant value increases. The rate law of the reaction is given by R equals to K times the concentration of a reactant. That is, the rate of reaction R is directly proportional to the rate constant K. Thus, it may be concluded that for a chemical reaction, by lowering the activation energy and increasing the absolute temperature T, the rate constant increases, and thus the rate of reaction also increases.